Hello everyone and welcome to the CSE116 Task 3 overview. In this task, we're going to be making, you know it, Pac-Man. And this is a really cool task. We've gotten very far at this point and we're going to start learning about these things called decision trees. Now, this you guys might have already done the problem set by the time that this video is posted. So you've probably gotten some practice by traversing BSTs. This is different than BSTs, although the binary tree itself structure, it's still a binary tree, it's just not a binary search tree. So keep that in mind. We're going to be talking about that a bit throughout this video. Before we talk into anything specific though, let's look at the game, because looking at the game is going to help us a lot think about what we're actually making. So let's take a look. Here's the thing though. The game is so unbelievably loud and there's too many sounds for me to mute, so I'm gonna just play it with all the audio. But let's take a look and I'll visually react to it. So yeah, that was Pac-Man. As you can see, these ghosts have very unique behavior. They're chasing me, they're running away, they turn into like their weird state. So this is going to be very fun because we're going to make the behavior of the ghosts through decision trees. So now that that's been looked at and established, we could actually get into some stuff. So binary trees, right? We all know them by now. I say binary trees overview here. I'm not going to go too much in depth exactly to how binary trees like work in terms of like memory and all that, but we are going to have to talk about them because that's what decision trees are all about. So I'm sure you guys all know by now the way to traverse binary trees, because you know you've probably practiced it with your BSTs already. So we all know about recursion, right? Elephant in the room, recursion. So why are we using trees? They tend to be very useful. So yeah. And yeah, decisions, we're going to be looking at decisions. So let's get into it. Alright, let's touch back on inheritance for a minute. So we're going to be implementing a decision class, okay? And basically, all of our ghosts are going to follow a tree of these decisions, right? But here's the thing. A decision itself is going to be an abstract class, okay? Which, if you guys remember, it means that we're never going to make an instance. We're never going to say, like, decision equals new decision. Like, we're never going to create a decision itself. We're going to create subclasses of decision and create instances of those, okay? So, a decision has the following behavior. A decide method that returns a boolean, and a do action method that returns void. And we're gonna in the actual implementation we might pass some things into like do action and stuff like that and decide. But for now we just need to like conceptualize it. So decide is going to return to us a boolean that will tell us what direction we should travel in the tree. Now this is quite different than our BST behavior, because if you remember from our BST, we would know if we should keep going right or left depending on the values of our left and right subtrees. Because like if we were looking for like a value 4 and we were currently at 5, we would want to travel left, because the value of left is, if it's a BST, it's guaranteed that the value of our left subtree is going to be less than 5. Because left is always less than our current value. So that's different here. In a decision tree, we're going to be deciding left and right based on what the current node's boolean decide method returns to us. Okay, true means right, false means left. Alright, now, do action. So basically, at some point, we're going to run out of nodes. Like, eventually, we're going to get to the bottom of our tree. And that bottom node is called a leaf, and we'll talk more about that later. But once we get to that leaf, that's the only time do action will be called. So do action is only ever used if we reach it at the bottom of a tree on a leaf node. Okay, we'll get into more specifics about all that soon. But let's take a look at some examples here. So these are real examples from the homework. We have two example decisions here. First one is active. This is going to be the most top level. This is the root of our binary tree, which is a decision tree. And is active is going to override the decide method, and it will return true depending on the ghost state. Don't worry too much about like choosing the ghost state and all that. That's just basically value that you get to read from the ghost class. But depending on the ghost state is what this method's going to return. And then another example here is flee. Now flee is an interesting one because you might notice that it both overrides decide and do action. And I just said that like only one of them is going to be called. Like if it's not a leaf, decide will be called. If it's a leaf, then do action will be called. Now here's the thing. We could group behavior, both a decide override and a do action override in one class if we want to reuse that class for both a decision node and a leaf node. So we'll see in our example that in an actual tree, flee could be both a non-leaf and a leaf. Okay, we could make two instances of flee, and it could do different behavior depending on its position in the tree, which just tends to be really useful. Technically, we could write another separate class just for the do action method or just for the decide method, but this is just so we save some space. And you know, as you guys have seen by now, the engine is already big enough and has enough files. So if we could group things, we're gonna try to group them where we can. Okay, so yeah, as we know, we're extending the decision class with these two subclasses, you know, children of decision. And just so we clarify here, since we've learned about polymorphism now, I'll just mention this. Flee, if we make an instance of flee, since it is a decision, it could be stored in decision variables, right? That is polymorphism. The fact that we could store an object of type flee in a variable of type decision, that is polymorphism. We can do the same thing with is active and everything else we see here. These are just some more examples. You can look at those if you want. These are also in the doc, and I'm just writing some of them out. So chase, it's got kind of the same structure as flee. It overrides both decide and do action, which means we could use it in two different places of the tree. And it just, you know, chases the player, and it will decide if we should chase the player as well. And then we have scatter. It's just a do action, so this is different. This can't be used as a decision. This has to be a leaf node. If you make a class that only has a do action, that means that it will be a leaf node. And it just moves the ghost towards its scatter position, okay? So, like I said, with that we can make a binary tree, which will be our decision tree. So we start here at our root node. Like I said, is active is at the top of our decision tree. It's the very first thing that we look at. Now, if our tree just looked like this and we were done, then we'd have a problem, because the is active, since it's the only node in the tree right now, we would have to call do action on it, and do action, we don't really override it, so it's not going to do anything. So that would be a problem, and you know, of course we wouldn't actually do this. This is not our complete tree, so let's keep going. Oh yeah, so first of all, just some reiteration here. If is active returns true, like if it's the decide method returns true, we'll be going right in the tree. If it's false, we're going to go left, right, as we already said. And also, you know, just reiteration, but it's nice it's all on one slide here. If this node is, if its left and right subtrees are both null, which it is in this example, we would execute do action on this node. And, you know, of course we don't have a definition for do action. It's like still its method in the parent decision class right now. We wouldn't actually have a tree that looks like this, but that's just some definition there. So let's expand this tree a little bit. So here is actually, technically, would be a tree that works. So If is active, returned, if it's decide method, returns true. So let's say, that would have to mean that the enemy's state or the ghost state is chase or scattering. Then we'd traverse here, and we would execute do action on the chase method because its left and right subtrees are null. That's how we know that we should execute do action. So we would execute that. And then another way to look at it is if decide returned false, we would have to do the same thing for flee. Okay? So we could see how this is starting to turn into like, a decision tree. Like we're making decisions based on a Boolean from our children of the decision class. And once we make all the decisions we can, we execute the action that we end up in. So we'll keep expanding our tree, and we get these here. So this is basically the complete tree that is actually in the homework. I'm missing one node here. Like right where my cursor is above the first flee, there's supposed to be a dead node with another right tree extending from that. But I didn't have space in the slides, and it doesn't change things too much. It's the same concepts here. It would just be a little bigger on this left side. Okay, so now that we have all of these states in here, we can see what we mean when I mentioned that the flee and chase both have multi-behavior. We could create two different objects of type flee and use them for different purposes. So because this first flee is not a leaf, we will not execute do action. We will just use its decide method to decide where we should travel next in the tree. But if this returns true, which means, I know it's hard to read, but it means the ghost has a frightened state, we go to the right subtree, and we get into the flee node again. But this flee is a leaf, so we'll execute do action. So that's what I mean when I say like we're just grouping behavior for like for less files basically. But we could have a different class here, but we're just reusing flee because we're overriding both. Okay, so now we could get into actually going through some examples here. Oh yeah, so yeah, every node at the bottom row is a leaf because their left and right subtrees are null. That's what a leaf is. You guys probably know this, but just for reiteration, a node with a left and a right subtree that are both null is a leaf. And those are the only nodes that get do action executed. Okay, so we have a ghost here, and it's... I'll change that over here. And its state is currently chase. Okay, so if the ghost state is chase, then think about it. We start here. Alright, we're at the is active. We have to start at the root of the decision tree. So you might want to go through this example in your head for a second and see where we end up. This one's not too hard, but let's go through it. So we start at the is active. We are the program right now. Okay, we are in the is active decision. First thing I'm looking at, I'm not even looking at anything else. In my code, I'm like, okay, am I a leaf node? The answer is no. I have one of my left or rights is not null, so I'm not a leaf. Okay, so then I look at my decide method and I execute that, and I got returned true because the ghost state was chase. Okay, so that would mean I go right and I end up here. Again, first thing I'm looking at, am I a leaf node? Nope, I am not. We execute the decide method of chase, and we get returned true, because it returns true if the ghost is just in a chase state. And then we end up here. And since, we are a leaf node, we now chase the player. Awesome. So this is how the decision tree works. I'll go through one more example. Okay, the ghost state is frightened. So we start in the is active node. Then we... Again, am I a leaf? I'm not going to go through this all again, but am I a leaf? No, I'm not. So I decide, and I get returned false because the state of the ghost is not chase or scattering. Don't really care what it is, but it's not chase or scattering. So we move to the left. And now, am I a leaf? Nope. So I decide, does the ghost have a frightened state? It does. So decide returns true. I go right. And up here, I'm a leaf. execute do action, the ghost moves in the random direction. Awesome. So these are examples of decision trees. Also, I have this one more example here. If the ghost state was not frightened, then we would be in idle state instead of moving to flee. And it would change like that. Like if the ghost state was rapidly changing, our decision tree might look like might be doing this like frequently. But those are some examples. So this is like this is the image from the doc here, of what the actual decision tree looks like. And as you see, I just left out this dead subtree here, but it really doesn't make too much of a difference. You would just have to add one more relation here. And yeah, like it's basically the same example. If we just extended that out, I'm sure you guys would be able to run through it just like we were just running through it. So yeah, that's pretty much all I have to say about the design of a decision tree. And now we could look at some more specifics in the doc. All right, we're in the doc. Let's get into the nitty gritty of it. So you know, we know the drill. You guys should have already read all of this. Ideally, you would have done the problem set already by now. And now it's time to get into the learning objective of the game features. So, as we know, we're using the same game engine, file structure, all that stuff. We're building it in there. First things first, we should probably change the app.configuration game to Pac-Man. You know, we've done this before. We've changed it a bunch of times. Same thing with this test task 3.java class that you guys have to download or copy and paste into your files there. I've done this before. If you guys are confused about how to do that, take a look at one of the previous videos. Yeah, so we have to use utilities found in app.gameengine.utils.pacmanutils. They're very useful, so keep that in mind. But we have a method missing, so you know we could click on this link, we could copy this method. You know, we only really need to copy this method. You should copy the comments up here as well, the documentation. It'll just help out in general. I would just copy and paste this one because it's pretty simple. So I'm just gonna do that for you real quick. Show you how to do it. Just go Pac-Man utils. You know, this right here. You know, all this stuff. Just find some place to put it. I don't know. I'm just gonna put it at the bottom and paste. Boom. Now we have it. So this will be useful to us when writing our stuff later. So let's move on. Yeah, so as the doc says, and like I'll be honest, it looks like a bunch of stuff that we got to do in this task. Like there's so many files, but there's a very like normal pattern with this. The difficulty isn't too hard. Like the difficulty for making one decision isn't too different from another decision. It's just more of a bulk of like it's more like volume of stuff you have to do as opposed to like density. Okay. So you guys should read through. Yeah, and again, I assume that you guys have read through all this before watching the video. So we have to go through these classes here. These are all the classes that we'll have to modify, but we will have to create some as well. So yeah, it is very important that we read through all of these before implementing anything, at least for all the decision parts. Like, again, so the decision stuff ends, like, right here when you see this tree. It's a lot, but it's really, like, conceptually, things don't differ too much from each other. We went over, like, what a decision tree is, and we just have to implement it. So, a decision tree, as we saw, it's a tree of decisions. So, again, in this visual here, this whole structure that I'm dragging around here is a decision tree. And then the individual nodes are the decisions themselves. So, if we go through this one by one, we have to first build the foundation of everything, which are the decision and the decision tree class itself. Yeah, so, of course we should start here. And this stuff, like, you guys have pretty much done all of this stuff already. Like, it's just making a class. Like, it's simple. There's nothing too complicated about it. The one thing that might be a little new is the abstract methods and the abstract class that we have to make in decision. So keep in mind, a decision is an abstract class that has two abstract methods, okay? Because we never want to make a standalone decision. What would that even do? It would be useless to us. We only want to make new versions of decision. Okay, and the whole reason we do that, by the way, is so we could utilize polymorphism. And I'll actually write out an example of that soon because it's helpful to see. Okay, so decision tree. This, like I said, is the class that's going to actually hold our decision tree data structure. So, as this doc mentions earlier on, we're going to be using a binary tree node. Okay, so it's similar to when we used a linked list node in earlier tasks. We have to use a binary tree node, and you might expect what this takes: a left, a right, a value, a left, and a right. And the value in this sense is always going to be a decision. Left and right are going to be other binary tree nodes of type decision. So, decision tree has a method named traverse, and that's going to do what we did earlier on. So, if you remember, like when we were going through the tree and like watching those like decisions like turn green and all that, that is what traverse is going to do. Okay? So, it might be helpful to visualize that when writing this method. It's doing that, and it's not too like complicated. It's just you have to understand the pattern. Once you understand the pattern, it's not as hard. So we'll also be overloading that traverse method, but it's not changing the behavior too much. We're just calling our other traverse method that we already made, and then calling do action on the return result of it. So traverse is going to give us a decision that we expect to be a leaf, and we're going to be calling do action on that leaf. So, as we saw, like in the examples, we are going to be calling do action on the bottom of the tree when we get to our leaf. And until then, we have to keep calling decide and keep traversing the tree. Okay? And I'll keep making this distinction just so you guys make sure you know it is way different than the way you traverse a BST. Doesn't even make sense to traverse this like a BST because how do we compare two decisions? That wouldn't make sense. So make sure we're keeping that distinction, okay? So then we actually get into making the decision classes themselves, which are most of the ones that we saw. Besides idle, dead, we've seen most of these already. So again, make sure we have the can act method because we're going to need to be using that. And then it's basically just time to start making decisions, right? We just keep making classes and follow the same structure that we saw on the slides. And, all we need to do, this is the nice thing about object-oriented programming, is like we could break these problems down into very small individual subproblems. So we're tasked with making each small behavior of each decision, right? And then once we have those, we could expand out and then assemble those in a tree and then have the logic just happen to work with our traverse method. It's really nice. And this is why we use this type of structure here. So we have a bunch of implementation details for each of these chase methods, scatter methods, and the content of them isn't as hard as some previous task content. It's really just some basic behavior that we have to decide and call with do action. And some of it's repetitive too, like flee and chase are pretty similar. So that's some stuff to keep in mind. I'm going to show you guys where to build these decision classes just in case it's confusing. It does say it, but just so it's very clear, app.gameengine.model.ai.pacman. So we have to create these packages, and Doc says this, but remember, packages are just files, right? That's all we have to think of them as. So app, okay, .gameengine, are you good so far? Model, and I'm missing the AI one. This is because this is a pretty young version of the tasks, but if you have AI, great. If not, create the package, right-click, new package, AI, and then we want to create a new Pac-Man package. So Pac-Man. That's not what I meant to do. All right. Anyways, so we have AI.pacman, and now we have to start making decisions. First one here is active, right? Idle, and of course I'm not going to make these all for you, but I do want to just show a quick example here. I'm just going to create an isActive class, but I'm not going to actually implement any functionality for it. So I'll just name it isActive. Not going to add it to anything. But Remember, is active extends decision. Okay, so it's a child of decision, right? I'll also just quickly stub out the decision class here. Okay, I fixed this file structure here. I don't know what was going on before. But decision will live in AI and is active will live in Pac-Man. So we have these here. Now, of course, decision is pretty wrong. We have to make that an abstract class, and then we have to make abstract methods inside of it. But I'm not going to do any of that right now. What I am going to do is just show, like, okay, first of all, we can't make instances of decision. Like, we know that we can't do that. So we would extend decision, right? And now that we've extended decision, I'm going to show one last thing, which is the decision tree class. Now, we know that we have to make, and of course, like, these are not the implementations. There's nothing inside of these. There's stuff that you guys actually have to do in there. But I just want to show the power of polymorphism for a second. Okay, so decision tree will have a binary tree node of type decisions, which this is our decision tree. You can name that whatever you want, but it should probably be, like, pretty good. Maybe not the same name as the class, but maybe even root's a good name for it. Okay. And then we want to make a constructor, and I'm just doing this to show the example. Like, this is not following the doc at all. I'm just going off of, like, I believe there's parameters in the constructor that you actually have to make. But I just want to show this one thing. All this that I just made was just to show this one example. So, even though this binary tree node is of type decision, we could initialize root to a new binary tree node, right? It's of type decision, but we can initialize it to a new is active. Whoops, is active. Okay, and then we could just do nulls for now. But I don't get any errors here. And you might be like, some of you like, this makes perfect sense. Some of you might think that, like, this doesn't make any sense because this is an is active class. This is a decision. Remember, is active is of type decision. And we can see right here, is active extends decision. If I hold control and click on is active, it is a decision because it extends decision. And because it is a decision, it can be stored in variables of that type. Okay, and if we could even click on binary tree node and see that it takes a generic type A value. Okay, and in this sense, A is a decision. So the A is a decision, as I just said, in the binary tree node class. So it's a variable of type decision, which means is active is an object that could be stored in a decision variable. Okay, hopefully that makes sense. And this should hopefully clear up a little bit of how, like, you're going to assemble your tree and all that. But I'm not going to go any further into this. I just want to show that basic example there. Don't follow all of that because you actually have to write stuff in there. You could, like, make those classes because you have to make those anyway. But yeah. So I won't go into specifics of writing all of these methods here because, like, this is the actual learning objective portion of the task. But it is helpful to know how this decision tree works, how it's actually going to traverse and all that, and the fact that all of this works on polymorphism. So that's the main bulk of decisions, okay? And decision tree stuff. We also have to make, like, a ghost class or modify ghost class, which isn't too hard. It's basically just changing it to work with the decisions. And an agent, which ghost is a child of an agent of the agent class. So yeah, but the second portion of the task is going to be making the inventory for the sample game and the roguelike, which you're going to work on next task. So we'll be able to see that though. And this is a big one that works with polymorphism as well. We were going to have items and pickups that extend collectible, which is also going to be abstract. I could show how this works now. Okay, for this example, I'm just going to simply change the potion to potion pickup in the sample game class, just so we could test all the features. So, we start the game here, and we're met with these two enemies like usual. But if I get hit by this guy a bit, right, I'm pretty low HP now. If I pick up this potion, it's in my inventory, right? So before I use it, I'm going to go to the next level. All right, now I have this axe. Now I gotta do this kind of quick. So I could press tab, and you can see in the top right, I'm swapping items. So I have an axe now. Actually, I'm gonna save. I'm gonna keep my health low for now. Okay, so I'm gonna make it to the next level, and now I'm gonna go for the magic pickup. So I just gotta get there. Okay, so when I get the magic pickup, you could see that I could cycle through all of these things in my inventory: axe, magic, health potion. You can see in the top right over here. I know it's probably kind of small to see, but yeah. So I could fire the magic one. I could use the axe. The magic one's way faster, but does a little bit less damage, I think. So, but with the potion pickup, now if I use this one, okay, I gain health, but now the potion's gone from my inventory, right? So this is the kind of behavior that we expect from the inventory behavior. We want to be able to remove items, but still keep the order and everything of the other items, still be able to use the other items, and like all that. So yeah, the pickup portion of this task, like all of the items that you actually pick up and use, is not the hardest part, because this is just back to inheritance stuff that you guys have been doing in polymorphism. So you know, all these things are going to extend collectible, like axe pickup, magic, and potion pickup. They all are collectible items, so they're all going to extend collectible, which is like, you know, all the things that we applied with you know, subclasses of decision, extending decision, like it works like the same behavior. There's it's an abstract class, there's abstract method, you know, it's the same kind of workflow. We just change the behavior per pickup to do something a little different. Now, I'd say the most like involved part of this task is definitely going to be making the inventory. And the reason for that is because you get to decide how to implement it. So, when doing this, you should really consider all of the data structures that we've looked at, you know, all of them. So, like, and just go through and see which ones you think would be best for implementing this, okay? The number one things to consider for this is certain actions such as remove active item and cycle inventory. Right, those two are big, are big methods that might change how you want to implement things. Right. Um, okay, if you're cycling the inventory, how do you want to handle that in your data? So keep in mind, we've talked about array lists, linked lists, you know, binary trees, but you know, let's keep it simple. So yeah, just you can do it however you want as long as it works. We're not going to be checking your actual like direct implementation. We're just going to make sure that all of your methods do what we want them to do, right? So how you actually store the data could be way different, which is why like I'm not going to talk about it too much, because it's up to you to decide, but I will show like some behavior here. Okay, so here's my super basic inventory. Um, and these boxes just represent how I'm deciding to store it right now. Like, I'm not saying this is a linked list or an array list. It's just data right now. So the thing about the inventory is that you have an active item, and somehow you need to decide how you want to keep track of that. So this arrow represents my active item right now. So if I were to press tab on this inventory, my active item would go here. Okay. And if I were to press it again, now this is my active item. And again, it should cycle around, right? So that's every time I'm pressing tab, I'm pressing cycle inventory, right? And this is what it's doing. Now, here's the thing though. If I were to right here to say remove active item, then this would get removed. My active item would let's pretend that's not there. My active item would go here, and then when I hit cycle, I'd go back here, and then here. You know, it should work just as expected, right? Like if you were playing this game, you would expect it to work this way. So you should build it to how you expect. So, and the specifications, for example, like when you add an item, adding an item will never change the active item. So don't switch your item, your current active item, when you add an item. Like if my active item was here, and I added an item, it would probably just go on the end down there, right? And it should keep working like this dynamically. So keep in mind, like, just I would really try to design this like how you're going to implement it before you actually start typing code, because you might waste a lot of time like going back and forth with approaches. So I would like just try to think it through first, and then once you get something where you think it kind of makes sense, try to implement that. And then other than that, everything else is pretty much stuff that we've done before. Like getters and setters, get active item, stuff like that. So you guys should be able to figure most of that out. And then we just have to change the level parser to read more static objects. So again, we've done this before. We could look at you guys could look at like another task video if you want me to go more into talking about the how to read static objects and how to change some of that in the level editor. Um, yeah, and so other than that, the main big thing that matters about testing is that you guys actually really use your test decision class that you have to make for the testing utility. Um, Trust me, it is way better if you make your decision tree with test decisions. The reason for that is because you'll actually be able to like manually choose where a decision, like if a decision should go right or left, because otherwise you'd have to load up a test case with like a player, an enemy, all that stuff, and then like perfectly set them to the exact conditions you want, like with the ghosts and whatever. It would be a real hassle. So if you don't want to do any of that, which is like way more annoying, just use your test decision class because you can manually decide what it does. Like when you create a new test decision object, right at that moment you can decide should this node go right or left when the decision tree traverses it. Okay, so definitely keep that in mind and definitely do that. And then yeah, like before, the main big methods here are cycle inventory and remove active item. Add items there because that one's pretty big too, but I'd say cycle inventory and remove active item are the ones that make you think the most. So those are the ones that we have you test. All right, and that should be pretty much it for this task. I know it's a bit of a longer one when going through like the decision tree stuff, but hopefully that was helpful. And hopefully the inheritance stuff for the pickups isn't as bad. And yeah, pretty much good luck with the task, and I'll see you guys next time.